Okay, so we have seen the first two parts of the tutorial. We have seen the IoT fundamentals and IoT stream mining algorithms, and we have seen the case study of social network analysis. And now we're going to look at these two case studies, the predictive maintenance and the secure IoT stream mining. So yeah, just to remind you, we have the slides in this site, Google.com site, KDD 2017 IoT. The slides are already there, so if you look at the slides, you will see that now they are in these 3 files. So we had to put in 3 files because it was a file too big, but now you have the slides there. Okay. Okay, so let's start with this third case study of predictive maintenance. So, yeah, what we're going to do is that we're going to first look at the problem, and then we're going to look at anomaly and novelty detection, and then we'll see how we can do this failure prediction. Okay, so let's start about what is predictive maintenance. So basically we have 2 types of maintenance. One is the preventive and the other is the predictive. So the difference is that usually in the preventive what we do is that we don't look at the current state of the equipment. What we are doing is that we are doing a maintenance periodically. We can do it every, for example, imagine that it's a car, so we can do it every 10,000 kilometers, or we can do it every 3 months. So this is something that it does not depend on how the current state of the car. The predictive maintenance, the other side, what we are going to look is at what is the current state, and then, yeah, for this we need sensors, we need to look at the data, and then once we know this, we'll try to predict when something is going to fail, much before it fails. So this is the main difference. So usually preventive maintenance is very good at the beginning. Imagine you have a car, it's going to be very good at the beginning because everything is new and we can do only this preventive maintenance, but once the machines they get much older, then it's going to be much more difficult to know when we are going to have a failure in some parts of the machine. So yeah, this is going to be our goal. So we know that this is a graph where we see that when a failure happens, so we see that at the beginning, yeah, something happens, the failure starts here, then we look at that, we can know this using the ultrasonic energy, we can detect that something is happening, then also with the vibration, we can see that something anomalous is starting to happen, then we can look at all analysis, see that really is happening, then noise, and then at the end here is when it starts to have this mechanically loose, and finally at the end the final damage. So yeah, we know here that it's failing, so our goal is to maximize the distance between the prediction moment and the failure moment. So we would like to do the prediction much before than it really happens. So yeah, to do this, we have different sources to look at the data, what are using sensors to know what is happening. So we have this based on the vibration, so we can use these sensors to know that there are some vibrations that are happening now that are different, especially for pumps and motors. With infrared, we can look at the temperatures and see if the temperatures are changing, or acoustic analysis, we can see if there is noise that is something different before, and we can also look at gas or liquid leaks. And finally, with oil analysis, also we can detect if something is changing on the size of the particles or in the structure of this. So we are going to look at a specific example. This is going to be the doors of the trains. So this is an example where now it used to be very simple mechanisms that were manually operated, but nowadays they use a lot of sensors, and also the new ones that are coming right now, they are also connected to the internet. So nowadays we have a lot of data, a lot of sensors, and we would like to see how we can do this predictive maintenance over this system. So yeah, the goal is basically that when a door fails, this is going to provoke some problems. So it may cause delays, it may cause satisfaction from the customers. So it's going to be really a problem. So it's very important to try to optimize and detect failures before it happens. So yeah, this is why predictive maintenance in this case is really important, and specific for these companies. And also there are specific directives of the European community on trying to make this transport system safer and more coordinated and efficient. So the goal here is that we try to build a machine learning system that is able to do this, to anticipate these failures. Okay, so this is going to be the goal. The interesting thing is that, yeah, it's not only detect that something happened, no? That a door, we had one abnormal functioning. So it's going to, because it could be that a person is opening or closing the door manually, so then it's not a failure, it's only that is someone. So what we're going to look is not only at this failure, we're going to look at this sequential failure. So this is important then to look at these sequences, because if it's only one point, we are not going to assume that this is a failure. Maybe it's only some a person that is closing or opening it manually. Okay, so let's talk a little bit about anomaly and novelty detection. So in that case, yeah, usually what we have is that if the behavior is something that is desired, then we are dealing with novelty detection, as Latifur explained before. But if it's something that is really undesired, then can be anomaly detection, so it's something that is different from the normal system behavior, or it could be an outlier if it's different, if the behavior is really different from the rest of the objects. So in that case, yeah, we are going to look at anomaly detection, and we are going to use outlier detection methods. So there are different approaches, so we can see that as supervised or semi-supervised or supervised. So if we look at unsupervised, there are simple methods, statistical based, like using box plots, and then looking when we can suppose the data corresponds to a Gaussian, and when it corresponds, it's outside the normal zone, we are going to say that this is an outlier. We can use clustering methods, or we can use density-based methods. So when a method is really, it's in a place where there is no density of points, so we can consider that this is an outlier. We have semi-supervised, that could be using autoencoders or using these one-class classifiers. Or it could be really, we really have a lot of label data. We have used the supervised method as neural networks or multi-instance learning, where we are using bag of instances, and we have one label for each bag of instances. We are going to see some of them in more detail later. So let's go to the case study. So what's the data that we have? So the data that we have are sensors that we have from the pneumatic valve. So the idea then is that we are going to look at the open and close faces. So as you can see in the open, basically what we have is that we have the pneumatic valve that is giving this pressure, and then the vane is opening in that direction, but then when we close it, basically the other way around. So here the pressure goes to the other side, and then we move to the other side. So the data we have is from this September to December 2012. It's around 500,000 of observations. This data from North Railway in the UK. And yeah, we have, it's an unlabeled data set, but then we have some labels from experts that they give us information where we have these failures. So the first thing that we need to do is to transform the data. So how we put this data into instances with features so that we can process them using machine learning. So in that case, yeah, each one of the observations is going to be or open or a closed door cycle. And then what we do is that we are going to have 5 attributes. We are going to create 5 equal length bits. And then we are going to take the average value of this. So imagine that this is the data, this is the pressure that we have. We are going first, the data, we are going to put that in 5 bits. And then from these 5 bits, what we are going to do is that we are going to look at the difference between the pressure of the two chambers. Okay? This is the data that we are going to use. as we see, then if the difference is positive, this is going to correspond to an open cycle, and if the difference is negative, then this is going to correspond to a closed cycle. So we have 500,000 pressure readings, but it's going to be really only 4,600 door cycles, where most of them, half of them are open, positive, and the rest is going to be negative. Okay, so if we look at the average of this, so we see that the average is changing, and we already see that there are some specific changes that is going to give us some hints of what is happening. So, yeah, so if we look at all the total cycles, we look at how many were abnormal. We see that basically from these 4,600, we have around 4%, 5% that are abnormal. Okay, so these are the ones that are abnormal. If we really look at the failures, what we see that we really have only 3 failures. So this is the information that the experts they give us. So we have these 3 failures in 3 different weeks. So we see that the first, it's we have 7 abnormal cycles for open and 2 for closed. Again, in this other failure, we have also open and closed. But the interesting thing is that in this one, the last one, we have only abnormal cycles in the open, but not in the closed. Okay, so we have now this data. So we have divided it between two data sets, between the ones that are open and closed. And then we want to predict the structural state of the door, if it's normal or it's failure. So we are going to use this 2-step approach. So the first one, what we're going to do is that detect if a cycle is normal or abnormal. And then the second one is going to be, we're going to detect if the sequence of cycles is normal or failure. So in the first one, if someone is opening a door, then this is going to be abnormal, but it's not going to be really a failure of the door. It's only a person that is pushing the door. So yeah, this is really why we need these 2 steps. So the first one, we are going to see what are the cycles that are normal or abnormal, and the second one, we are going to filter these ones to only have the ones that corresponds to a failure of the door. So yeah, for the first one, so we're going to detect if they are abnormal. So this is a standard layer detection. So we are going to use supervised methods and semi-supervised methods, and we are going to optimize the detection error. Okay, the detection error is going to be based on the false alarm rate and the impostor pass rate. So it means this is like false positives and false negatives. So we are going to detect what are the errors, and then we want to minimize this error. And again, we're going to use this reduce false alarm because we want to really only take the real ones, because the ones that, for example, once there is a failure, we are going to have some detections, and we should remove this from the measure. So this is why we use this reduce. Okay, and then for the second step, so remember the first step we know when is normal or abnormal. In the second step, we want to get what are the failures of the system. So for doing this, we are going to use this low pass filter. So the idea then is that we want to remove the abrupt changes. Okay, so when there is an abrupt change, this is only one time. So one person is opening the door, and so it's only going to be that. So we want to filter. We want to remove these high frequency steps. So we are going to use this low pass filter. In this case, it's going to be very easy. So what we have is that we have this variable y, and then what we do is that we start with 1, and then for each new xi measure that we arrive, we multiply it by alpha. This is the smooth parameter, and then we multiply the previous value, y times I minus 1, by 1 minus alpha. Okay, so then depending on the value of alpha, so if alpha is really high, we are giving more importance to the new entrances, and if alpha is really small, then we have more inertia, and we are giving a little more importance to the previous values that we have. So this is an important decision of the low pass filter, is to decide what is the value of alpha. And yeah, how we decide if we have a failure, we are going to decide if it's a failure if y is less than 1/2. let me also see some experimental results. So yeah, basically the three things that we want to see in these results is that it's really this low pass filter beneficial. What is the impact of using self-feedback versus expert feedback? So of course, using expert feedback is always the best option, but it's really, really expensive. And so this is why if we can use self-feedback of the system, that could be really useful. And finally, what is the impact of using previous information in the detection system? Okay, so how this is done is that we train the system with the first 4 weeks, and then after that we are going to decide how we continue updating, how we continue to update the models. So yeah, the methods that so the different memory models that we're going to use is the first one is the static, so we use the data from the first 4 weeks, and that's all, and we don't update the model anymore. The other one is that we use a slide window, and then in this slide window what we do is that we move the slide window, but then we can add the information with expert feedback or with self-feedback. Self-feedback means feedback from the same system. Or we have this growing window that what it's doing is that is not removing anything from the past. So it's growing, but in that case you're using self-feedback. And the learning models are going to be this ensemble of box plots, there's a statistical method, these autoencoders and online classifiers. And then we switch the alpha parameter between these values to see how it works. Okay, so yeah, just to remind how this ensemble of box plots works. The idea in this case is that we have these 5 bits. So this is the information that we have for each one of the attributes, for each one of the bits. So this is the points. Okay, in that case we have this gray and this red. So if only one of these, in this case this red one, if only one is a liar, then we're going to consider that everything is abnormal. Okay, so in that case the gray all are inside the normal condition, so everything is going to be, we're going to consider that this example is normal. But this one is only one of the bins, so this is why we call it ensemble of box plots. Only with one, then we are going to suppose that this is an outlier. The other method is this autoencoders. So the idea here is that we use this neural network where we are targeting the output is going to be the same as the input. So the idea here is that if our input data is really normal, so it's really the same that we use to build the autoencoder, we are going to have the same output, the same input at the output. But if really this is an outlier and this is really different, we are going to notice that, because then the autoencoder is going to produce a different output that's going to be different from the input. So this is the way that using this autoencoder we can discover if this is an outlier or not. Finally, we have this one classification, one classifiers. This is one SVM. This is based on the idea of we want to have a spherical a sphere with all the points that belong to this one class, and we want to minimize this radius. And finally, this one class classification. That the idea here is that we have these normal points, and then we build from these normal points, we build artificial points, and then we have it as a two-class problem, and then we can use any classifier to deal with this problem. So this is the learning models. So yeah, just to see if the low-pass filter works or not, what we see is that if we look at the number of false alarms, if this is the number of false alarms that we have before applying the filter. If we apply the filter, what we see is that we really reduce the number of false alarms from 66 to 82, or from 34 to 100. So it's really working in the sense that it's reducing the number of false alarms. Interesting, if we look at the detection, so we know that the 3 failures that we have is these 3 gray areas. So we have this one here, this is for open, and for close we had only one that is here. So in that case, if we use the slide window with sliding window with the feedback of the experts, sorry, with the self-feedback, and we use the example box plot. What we see is that we are detecting, because we are detecting when this is lower than 0.5, so we are really detecting the two failures here, we are detecting this one here, and we have only these two false alarms. So it's not, yes.
What is the difference between this method and the basic high-low? Because the anomaly you caught here, evaluate the percentile and sort it, you still get the extremely low value as an anomaly. Based on the one class SVM, to my understanding, is very computationally expensive. We basically store this data by descending order, increasing order, calculate the percentage. We still get the same anomaly results. There's no big difference.
Yeah, so now we will see what happens with the online, with the one class classifier.
Okay.
So the idea is that using boxplot, this is much simple. And in terms of false alarm, what we are going to see is that this works fine. If we look at using the autoencoder, here we are not having false alarm. We are detecting these two, but we are not detecting this one here. Well, the nice thing is at least we are detecting this failure here in the open, so it's not really bad. The problem then is when we are using the online SVM classifier. Then we are detecting, but then the number of positive false alarms is really high. So this may be a problem. Yes.
Quick question. So here is this still the two phases methodologies here?
Yeah, here we are using with the low pass filter. So this is the final result. So here, the goal is to find this failure. So the goal is to find only this. Only to find these three. So this should be the
so below the threshold.
The goal is to find this one, and this one should be here, and not have false positive. So that should be the idea.
I have a question about the first step in your two phases strategies. The question is about the abnormal, because you want to figure out the abnormal stabilities. Do you have any observations or experience that sometimes the store becomes abnormal, it's an outlier, then after several days it's back to the normal? How stable is your abnormal? So that's how I call stability.
Okay, so in these cases, what we have is that we have this sequence. So if it's only one, if it happens only one, then this is not going to be, it's going to be filtered, and then it's going to disappear.
Right. So
it's doing this low pass filter. What we are giving is that we are removing all these things that was more noise or was only one. It was not really something that was really a failure.
Yeah, because in our problems, for example, the smart meter data, and we are monitoring the power consumptions. Then for this household, suddenly the whole family has gone to vacation. Then what you observe is your power consumption, the water suddenly dropped to a very low level. Then 3 days, at this time, if you're using the window, if your window is too narrow, then it becomes an outlier. Then 3 days later, back to the normal. So there's a lot of these things happening. So I'm wondering if you have the similar.
I think it really is similar in the sense that imagine that this is only something that happens only for 1 hour or for 2 hours that the water. This is then it's not really. You cannot want to detect that, but if you want to detect it, there's really something that is going to be stable over time.
Right,
so then
it becomes that
then depending on what your needs, you can use this filter one way or the other, just to filter the information that you want. It basically is to reduce the abrupt changes that you have. No? Imagine that you have abrupt changes that you are not interested, so you only want really the changes that are more stable. Then using this low pass filter, you can focus on that.
Thank you.
Can we change from the timestamp to the indices as the x-axis?
Sorry?
So my question is, we are using time like the x-axis. If we use indices, number of observations as the x-axis, we have axis issue. Why we use the time here? as.
Well, yeah.
Sometimes the machine is running, machine can be off, right? So you use time, we're probably talking with different modes, different activities. Right?
Yeah. So this is how
Time is.
Yeah. I think that depends also on the specific case and how you. Yeah. Maybe in many cases, yeah, time is not the right measure, and then you can. Yeah. That's. Well, it depends on the specific. So here it was more just to show the different combinations and then see what is the best. So how they work, and basically, yeah, what we see is that if we use this on one class classifier, we are detecting them, but yeah, we have really a huge number of false alarms. The same here. We use the other one class classifier, so still it's not. So yeah, basically, the idea is that using these ensemble box plots and these autocolors, this works much better than using the one class classifier. Using this low pass filter, what we are doing is that we are reducing the number of false alarms. So this is something that it works. And in terms of self-feedback and expert feedback, what we see is that expert feedback is something that we would like to have, but usually what we see is that using self-feedback, the system works fine. Then when we change how we do the training windows, if we use the static, what we see with the static is really that the number of false alarms is really getting high, so there's a need to update the model. So we cannot use only the models from the beginning. We really need. So we change these and we use autocolors. Again, still it's not working. And if we use when we start to use the growing window using the self-prediction, this still works much better. We have a small number of false alarms, and we are able to do the prediction of detect these failures. If we use we use the online one class classifier, we still get some more false alarms, so it's not really improving. So the nice thing that we get here is that really we need to update the model. So if we use only the static data at the beginning, this is not going to work. So using the light window works well. It could be nice really to have the expert feedback, but this is really expensive. But if we use this self-feedback, the system works fine, and we are still be able to detect the failures, and also we have a very small number of false alarms. Okay, so I think that just to summarize, so the idea is that we have this machine learning system that is able to predict this. It's divided into two parts. The first one is detecting abnormal cycles, and the second one is then detecting the failures. The second one is based on a low pass filter, and the first one is using an outlier detection method. Okay, yes, please.
How much time before the failure do you see this, before the door actually fails? Do you see this difference in the pressure sensors? I mean, how much time do you get from this in real time?
In real time, if we look at the data, so when we are able to predict that, it's in terms of 1 day or something like this. So the time it's really really small. So the thing is that it's in that case it depends on this data. We have this data of the sensors. So in that case, but what is really important is the system, because if we have really a huge number of false alarms, then this is going not to work. So it's, but if the system works, it could be fast to see, because then after we see the first signals that something is going bad, then we can predict it easily. Any other question?
This is univariate analysis, or this can also be applied for multivariate data?
It could be an interesting extension. It should be possible to do that.
Does the proposed method consider the correlation between different channels?
Not now. So in this case, it's only looking. So it could be a nice way to extend it and see. Nice idea.
And how do you retrain this model?
How we
retrain this model?
So in this case, what we are doing is that we are using the sliding windows. So if we use the sliding window, then what we are doing is that in this case, this is more a prototype, a use case. So in that case, what we are doing is that we are building this new system with this data from the sliding window. So we are getting the data, and then so this is how it is.
So you mean we train this model once and we can use this model for a long time?
No, so the idea is that we have 4 different ways. One is static, so we train the model only at the beginning, and then we have this sliding window where what we are doing is that we are getting more examples, and then we are removing the old examples, and then this growing, that is that we are not removing, so we are only adding these new examples that we get from the self-trained instances. Okay, so maybe now we go to the last case study.
So this is the last part of our talk. So now I'll focus on the IoT stream analytics. And for this work, okay, so this talk I will focus on the security part, and I will show you some current state of the art, and that heavily relies on Intel SGX to provide the confidentiality and privacy. So first I will introduce you some background materials. This is called trusted execution environment, and one of the example in the industry from Intel, they use Intel SGX security data extension. And I will present some of the work in this domain. In particular, I will focus on the secure data processing or log processing. For the IoT, generates humongous amount of data, how you can process those data effectively in a secure manner. And then I will show you, even if you use those trusted execution environment, there is no guarantee that you can avoid some of the inference type of attacks, like side channel attack. So for that, there is some work going on, so I will present those work, and those based on the data obliviousness and the randomization, and that way I will end my talk. So let me introduce you what is the Intel SGX means. Before going to talk about that, let me tell you that nowadays it is very difficult to trust the computing devices. It is possible that you are running your applications in a third-party cloud where you don't have any control, and the program you're running there, that program might be compromised due to the third-party software, third-party product you are using that might be compromised. Like for example, in a typical scenario here is a bunch of applications, and those applications will be run independently from each other. They will not interfere, and they usually run in a user mode or less privileged level. Then the OS operating system will be run at the privileged level. But there is a possibility that the operating system itself may be compromised. So, and then application wants to access communicate with the OS, they will use the system calls to move from a user level to the privilege level and run the code. Now there is a possibility that some of the apps might be malicious, applications might be malicious, and those malicious applications try to exploit the operating system vulnerability. Let's say in a server or in a computing device, you are running some OS and OS is compromised. So in that case, these malicious apps will exploit that vulnerability and start to take care of start to penetrate the system and then it will continue the attack to the OS, and then it will go to the other apps will be infected. So what I'm saying here, apps are not protected from privileged code attacks and so on. So the key point here is, even if your OS is compromised, the apps we are running or applications we are running, we want to protect that application. So is it possible? So our this presentation, we want to protect the applications in spite of even the privileged system code OS hypervisors, those are compromised. So there is a way you can do it that called trusted execution environment. So for that, the idea here is when the apps comes or application comes, we'll first identify the trusted part and the untrusted part. Trusted part will have the trusted code and the trusted data, and then trusted part will be run in a secure or isolated environment in the memory, what they call it enclave in case of Intel SGX. So this is the basic idea. I'm just trying to introduce you the first concept, background concept, then I will move towards how SGX can facilitate secure computation or provide confidentiality and privacy. So that's why I'm still covering some introductory concepts. So what I'm trying to say here, your applications will have a trusted part and the untrusted part. So application is built with the trusted and untrusted parts, and application runs and creates an enclave which is placed in a trusted memory, and trusted function is called, and code running inside the enclave sees the data in clear, external access to the data will be denied. So for example, what I meant, now I say, think about that. In this case, we don't trust we assume that your operating system or the hypervisor might be compromised. So it's still compromised, but when you run this trusted apps, part of the apps in an enclave area, then this OS cannot take care of this. OS cannot tamper that content and so on. So the key point here is application gains ability to defend its own secrets. So with this way, by dividing the applications into trusted and untrusted part, we reduce the attack surface area, and then with the enclave, we provide the security and privacy. And there are already some trusted hardware solutions exist. You may say, why don't you use the homomorphic cryptographic solution and so on, which is possible, but which is computationally very expensive and is not realistic to use in various settings. So that's why we're not using it. We are trying to use the trusted hardware solution. And there are a bunch of commercial products are there, and Intel has one of this, and it works on the commodity hardware. So in this work, in this presentation, I'll focus mostly on the Intel SGX. And this, it has a enclave area, an enclave applications, data application code, and then the enclave area will provide, will take care of the code and the data. It provides the confidentiality, integrity, and it has a control entry points. So what I meant, in case of Intel SGX, the assumption is all privileged software is maybe malicious. That's the assumptions they have. So that means your kernel or OS or a hypervisor may be compromised, and our goal is to facilitate or protect the applications by providing the confidentiality and integrity. And there's some work in this domain. And here is an example application layout. You have the trusted part and untrusted part. For the trusted part, you have a trusted code and the trusted data that will be run in an enclave area, and the enclave area covers the enclave page cache. And usually this is a protected memory, and this memory size per processor per machine is around 128 megabytes. It's not that big. And then untrusted part, untrusted code, and the data will be run in a typical memory and so on, which might be compromised and so on. But again, this OS, even OS is compromised, but OS still cannot access this area. This will be protected by the hardware key, and this key will come from the CPU. So there is a hardware key will be there, it will reside here, So once the enclave is established for a particular application where you will put your secure, where you will put the code and the data, the trusted code and the trusted data, that will be always decrypted by this key. So that way OS cannot have access this area, and also there will be a secure channel so that snooping attack is not possible. Okay, now there are, this Intel facilitates you some of the, when you establish an application, you need to make sure that the attestation will be taken place, and then we will have a data sealing and unsealing. That means store the data securely outside of the enclave, or so outside of the enclave means derive a seal key from the SGX hardware key and encrypt the enclave data using that seal keys, and then send it to the outside of the enclave. And vice versa, if you want to move the data from the outside to the enclave, then you will do the unsealing. Okay, now, so I just tried to give you some introduction about the SGX. Now I'm going to move towards some of the work going on in this area. So first, I will show you how the log, and this log can be generated from the systems or can be from the IoT devices, how we can secure them. And then there is some work in the cloud computing domain where you want to do some, run some MapReduce job. MapReduce is widely used for big data processing, and how you can make it secure using this SGX. That we'll talk about that in a minute. Then I will show you when you run some analytics algorithm, even if you use this trusted computing based or hardware based solution, there is no, it will provide you some sort of security, it will provide you confidentiality and integrity, but however, still it may be vulnerable to the side channel attack or some sort of inference attack. So how you can avoid that using some randomization technique, so that I will cover in a minute. And then also in network area, people are using this SGX to facilitate security and the privacy. So that I will cover also. Okay, let me tell you more about the log processing. So the logs are generated from the system failures, system analysis, network traffics, and so on. So our goal here is to secure the log. And experienced attackers want to steal the log information, want to change the log configurations, and then they want to modify, replace, or delete the log files. So our goal is to prohibit this. And here is the idea for this. So the log will be captured by the Linux syslog from the clients, and it will come to the server, and the server will parse it and do the filtering and identify the right content and then log it. And we want to put it into the persistent storage. So what is the objective of this log processing? The objective is to provide the confidentiality and integrity. In the security, confidentiality means no unauthorized access to the system logs and the configuration files. And integrity means once the log file is created, it should not be modified, it should not be tampered. So that's the two objectives we want to achieve. And we want to achieve these two objectives using trusted execution environment or SGX. And the threat model, here we're considering the local insider and the remote attacker. And remote attacker can be use the network connection, or the local insider can be have physical access to the system. And there are some solutions for this type of work already exist. You can use the hash key chain, which might be linear hash key chain need to be used, which will not be efficient, or tamper resistant software solution you can use, but it will require the code obfuscation. And then there are some hardware based solution, but again this will incur very high cost and smallest storage capacity it has. So what do the authors propose here? Hybrid approach. that uses Intel SGX. Again, Intel SGX runs on a commodity hardware x86 architecture, and then cryptographic protocol, the authors modify it using hash keychain. And authors show that the overhead is very insignificant, only 7%. Okay, so now the question is, once the log is generated, you need to run it in a secure area, what we call it an SGX enclave area. But recall that I tried to introduce, when I introduced SGX, I mentioned that SGX has a page memory which is only 128 megabyte in size. Usually the log usually big, so we cannot run the entire logging system inside the enclave. That's a problem, and also enclave doesn't have support for the system calls. So the second approach is, why don't you only protect the secret inside the log, basically the log messages and the logging code, but still it will not fit well in that 128 megabyte in size. So what the author proposed, hybrid approach. So they identify the trusted part and the untrusted part. So they identify the log messages and configuration files and the code that will be put into the enclave area, and the untrusted part will go to the typical memory. And protecting the high volume of system logs, they use the sealing and unsealing. And for the streaming, the log messages are continuously coming. For that, the author implemented the ring buffer. And for the verifying the arbitrary subset of logs, whether tampering happened or not, they use the block level hash key chain. So, what I meant, there will be a trusted part and untrusted part. Again, the trusted part will have the trusted code and the trusted data. So these are the trust enclave area. You will maintain the configuration file and the log buffer. And these are the modules the author implemented. And the other untrusted part will have this component. And authors show that using, there might be various attacks are possible. Like unauthorized log reading, that's avoided because it will be run in an enclave area. Compromising security key is not possible due to the enclave protection. Log tampering is not possible due to the implemented block level hash key. Log deletion, these are not possible. On the other hand, this is vulnerable for the side channel attack. And authors implemented a system with this configuration. And for the data set they use, these are the log sources that they use, and then you can see the size is around this kilobyte in size, and number of messages like this, and average size per log is this. And here, so you can see if you don't use the SGX extension, SGX adds additional overhead. So the performance the authors try to measure here, how much overhead the SGX will introduce. So lower overhead is better. So here the timing is reported. So if you don't, y-axis represents the time and x-axis represents various data set. So if you don't use the SGX extension, just to run it in a typical memory with no security guarantee. So in that case, it will take this amount of time. On the other hand, if you add the SGX, so it adds some overhead. But the overhead is not that significant. On average, overhead across all these data set 4.8%. That means if a particular application takes 100 seconds, then with this SGX it will take 104.8 seconds. So the authors show new logging system to protect the confidentiality, the integrity, and partition the logging system into the trusted and untrusted part. And show that the overhead is not that insignificant overhead, and the source code is available. So now the authors try to extend this work for the IoT framework. IoT, bunch of sensors, and generates the humongous amount of data, and that will go to the IoT cloud. And the goal here is to secure those data. So for that they use remote attestation first, and then the integrity of the customer using the data hashing, and they ensure the customer data is safe. Sealing and unsealing will be used. So what I meant, So IoT devices generates the data, and then IoT gateway will pass this data to the cloud, and the cloud where we will deploy the SGX to make sure that when the data comes, those data will be processed in a secure manner. It will confidentiality will be preserved, and that integrity will be preserved. So for that, SGX will be deployed here, and then SGX will create enclaves where in a secure region those data will be processed. So the trusted module will have this K module, encryption, decryption, integrity check, and those standard techniques. And then for to communicate with the outside world, the eCall and the OCall, these are the functions that we'll use, as I showed you before. So here you can think about IoT device generates some data, and then we need to store it into the secure storage. So the data will come to the enclave communication channel, and then it will go to the sealing and unsealing, and there it is coming from outside. We'll do the decryption. It comes in encrypted form. We'll do the decryption, and then we will seal it, and then before that we'll do the integrity check and seal it, and then store it into a persistent storage outside of the enclave. On the other hand, if you want to do some read operations for a particular content you want to read from the end, data will be loaded from the persistent storage, unseal it, and do the integrity check, and then extract the right data and deliver it to the requester. And for the experiment, the author uses a bunch of these IoT devices, and this is the read performance overhead and the write performance overhead. You can see when you use the SGX, the overhead doesn't add that much, so it's around 10%. So you can say SGX overhead is insignificant. And then when the data will be sent, it will be sent in a block form. So the block size is smaller. You can see if you use the smaller block size, that means if you have a large data set, that means you have to send many blocks. So in that case, overhead will be high, CPU processing time will increase, but on the other hand, when you have a higher block size, number of blocks will reduce for a fixed for a fixed size of data. So in that case, with the increasing block size, CPU processing time decreases or becomes flat. And then, so this is one work, and then I'm going to present another work where we want to run the analytics algorithm in a SGX to facilitate security and the privacy. And this work will appear this year in the European Security Conference. So the idea is this. Let's say you have a bunch of sensitive data. Those data may come from IoT devices or from other sensors or from any sources. And you want to store it into the third-party server, for example, in the cloud. And you may not have any control. You don't know who is running the cloud and so on. So an attacker may want to hack the system. There is a possibility that in the worst case scenario, that the server is compromised, that OS is compromised. In that case, attacker may have the full control on this third-party server or the cloud. But what I'm saying here, we are going to run it on the this cloud will utilize the SGX. Since it is utilized the SGX, even the OS operating system or hypervisor are compromised, but still the important analytics algorithm will be run on XGX, so that will give you guarantee that a lot of attacks are not possible. Attacker will not be able to carry out bunch of typical attacks. However, there is a possibility that side channel attack or inference attack is possible. So what I meant, so the threat model is this. So we are in the cloud, third-party cloud we are running, and it will be the third-party cloud, let's say, exploit the SGX. So that gives you guarantee that attacker may not be able to see the data because our code is encrypted, and it cannot access the SGX enclave area or where this analytics algorithm is running. However, from the system resources, CPU uses, memory, disk, bus uses, the attacker may be able to infer some of the side channel attack, what they call it. So here, what is side channel attack? You can think about this source code is publicly available. Let's say function f1 is called f2 function, and then after that f3 function will be called. And f2 function calls f4, and f3 function calls f5. An attacker may control, or adversary may control the page fault. So in that case, let's say page A, as an attacker, we may not be able. As an attacker, I may not be able to. I can only see the page, and then content I cannot see. It's encrypted. So, but attacker may control the page fault. So in that case, after page A, f1 function is internally. From this figure, we can see it. F1 function is called, and then page B contains f2, and then page D contains f4, f5. So as an attacker will see only that there is a page A access, then page B access, then page D access, and then this sequence will be accessed. Page access sequence can be observed by the adversary, and from there, given this source code, attacker can identify that function f4 is called first, then f5 is called next. So that type of information gathering is called side channel attack, and using that, attacker can do a lot of things, and this way attacker can carry out some inference attack and infer a lot of things, and usually in this case adversary will be very sophisticated. When you run some analytics algorithm, we want to make sure that even if you run it in a SGX environment, it will be vulnerable for the side channel attack. So the goal here is to defend against this side channel attack, and there are some work called data oblivious solution. So for example, in these functions, we are trying to return the maximum, right? Given two numbers, I want to return maximum. And this solution is non-oblivious solution because return value depends on the condition x and y. Value of variable x, y, and x and y will be encrypted from the attacker perspective and are placed in a different registers. Now, non-oblivious solution, if you implement like this, as an attacker based on the input, attacker can infer that which which value is the input now. Whether it's a greater or less, those type of things attacker can infer. On the other hand, if you have oblivious solution, for the oblivious solution case, variable d will be accessed regardless of the condition, because here I'm saying if x is greater than greater than y, then d equal to 1, if else d equal to 0, and then we are returning this. So regardless of x, y values, d will be accessed. So in this case, the solution is oblivious max. Now, in case of data analytics algorithm, like for example, supervised learning or unsupervised learning, like decision tree, we want to make sure that there is no side channel attack. Side channel attack should not be successful in this context, in the case of analytics case. So for the data oblivious solution, we said eliminate data dependency and memory access. One possible solution for data oblivious solution is when you have some queries, you want to get the access pattern, from there you want to infer, right? That's the side channel attack. So when you are given a query, you want to access all the array variables. So every time you will access all the array variables and give the particular results. So that way the attacker may not be able to infer anything. On the other hand, conditional statement case, access all variables independent of the conditions. And for data analytics case, we know that in case of decision tree, these are the public parameters and this is the private or confidential parameters, like the tree structures and the level of the data instances. So our goal is to preserve these confidential parameters, and here there are some work already in this domain to make it obliviousness, so secure data analytics algorithm. So for example, you have a decision tree like this, and you can see in this case this path is short, this lead node will reach here, but in this case the path is longer. So when the test data comes, and if you don't have a secure data analytics, then if the test data explore this path, from this path, due to the side channel attack, the attacker may infer that which path is exploring. So we want to make it oblivious. So for that, every task data, all paths from the root to the leaf will be accessed. So basically all leaf will be accessed. But before that, first this tree will be fully balanced tree. So in case of secure data analytics, the author, what they did, they convert this original decision tree into a fully balanced decision tree. These are the dummy data they had. And when the test data comes, they want to make sure that the side channel attack will not be successful. So for that, every time test data, a particular one test data comes, they will explore a particular path. Instead of returning that path, they will give all the paths from the root to the leaf. So that way, the side channel attack will not be successful. But there is a problem with this. The problem is, every time test data comes, you will explore all the path and then return the results for a particular right path. The level will be returned, but still you will traverse all the path. And ignore the level at the leaf, which are not part of the correct tree path according to the test data. Okay. So what is the problem with this solution? The problem is it is very computationally expensive. Every time test data comes, you will traverse the whole tree, and you also make the tree fully balanced. So if the large number of parameters are present, like very large decision tree, large number of variables, large domain size, then this method is very expensive. And in real life, some cases privacy is not that important. So if you so complete data privacy may not be always required. So the threat model here we are considering for the decision tree case, the data point itself and the higher tree, we want to make it private. For the name-based classifier this, and for k-means unsupervised learning, we want to make those private. So how we can do it? The idea is this: when the test data comes, we want to predict the class level. So we will generate. We assume that given the decision tree is given, and from there we build a fully balanced decision tree. And now when the test data comes, we want to, instead of exploring the whole decision, all the path in the decision tree, we will explore we try to do better. So for that, for the test data, we generate some dummy data instances. Given a test data, we will generate some dummy data instance and mix it with the given test data, and then process one after another and so on. So what we call it contaminated data means it will have the given test data, user given test data plus some dummy data we generate. And so for the dummy data generation is a straightforward. You can use the maximum minimum values, the range, and then randomly generate the data. So here this is input data, means not a training data. Keep in mind this input data means input test data, and we want to make it oblivious. So we will randomly generate some dummy data given this test data and mix it. And for the mixing, data oblivious sorting will be carried out. And then after mixing it, this contaminated data will process one after another, and some of them will have the true test data and some of them will be on dummy data. And so we create, as I said before, that the decision tree will be, the training decision tree will be from the training the decision tree will build, that will be balanced first. And given a test data of size n, we will generate L number of dummy data. Usually L is greater than or equal to n, and randomly shuffle the user given data with the dummy data, and then evaluate class level for each instance sequentially. If it is a dummy data, we ignore it. So that's very straightforward. And net-based classification case, also ignore the level for the test data. And for the k-means case, this is the unsupervised learning. So you recall that k-means is what? It has two steps. After initialization, when you do the iteration, each iteration, there will be a membership determination, which cluster it belongs to the test instance. I mean that data point, and there is no test instance here. And then update the centroid. So for the membership determination, the dummy data will be used, but for the update the centroid, we'll ignore the dummy data points. And the author showed here data privacy guarantee. So the trace variance means sequence of page access during evaluation of a data instance, and privacy variance will be gamma divided number of fake trace variance divided by total number of trace variance. And when there is no defense, gamma should be close to 0, and when the fully defense or oblivious solution, that means no side channel attack cannot be successful. In that case, gamma will be close to 1. And in this paper, author tried to show that if you set the gamma equal to 0.5, 0.7, you can achieve better performance in terms of the speed, but you will sacrifice some of the privacy, but that privacy you are sacrificing is in a tolerable level. So if you have in this case, n is the number of input test data and the L dummy data you generated from this, and gamma will be L divided by n plus L. Now for a very large L, where L is significantly higher than capital N, in that case gamma will be close to 1. So you are giving guarantee for the privacy, but on the other hand, if gamma is L equal to n, then in that case gamma will be 0.5. So in that case you are giving half of the security. The privacy guarantee. So adversary guess should be at most random when gamma equal to 1, but large L increases. The problem is we cannot use that. So that will be similar to a typical data oblivious solution. You will explore the whole. For each test instance, you will explore the whole tree. But larger L increase the execution overhead or the timing, so therefore, usually we set L equal to n or slightly higher. And authors show that they use, these are the data set they use. First two data set are the, first one is a medical data set, financial data set, and these are the data set they use, and these are the size, and these are the features, these are the classes they use. And then here they show that when you use the first approach, which is oblivious solution, that means you have to, for each test data comes, you will explore the whole tree. For each test instance, it observes this amount of overhead, which is very high. But on the other hand, if you selectively add some user dummy data and then explore the path instead of exploring the full path, so that overhead drops down significantly when you use this author's approach. And then for k-means, the result is a little bit a counter. You can see that for the k-means case, the results are very similar. The reason is k-means we are not doing any, there is no training and testing here, and we just, for the membership determination, we just avoid the dummy data, so that's why the result is similar. And then if you want better privacy, the time overhead will also increase significantly. But if you use the less privacy, the overhead will be reasonable. Okay, and then author try to show when they generate the input data, input test data, and then dummy data, how their similarity looks like. They're very similar to each other. So here for various data set, four data set they use, for each data set you can see similarity is very high. Okay, so this is, and then there is some work in the domain of networking. Software defined network, you have a bunch of controllers, and these are the local controllers, and they will communicate with the other local controllers through the inter-domain controller. And now each of this controller has its own privacy, own policy information, and they want to keep this policy information secure. In other words, they don't want to reveal this policy information outside world. But if you don't use, say, SGX or enclave type of secure region, there is a possibility that you can say, why don't you use homomorphic cryptographic solution? That's one possibility, you can use it, but that may not scale well for a large environment or setting because it's computationally very expensive. So alternative solution is, why don't you use SGX enclave and so on. So for that, we want to, that's the author, you try to use it. So each of local controller will have its enclave, inter-domain controller will have its own enclave, and those first enclaves will communicate each other and then establish the secure channel. So for that they do some attestation first, and then the policy and topology will be collected and through a secure channel, and then shortest path will be calculated and be shared, and those type of things they did. And that way the author showed that this using the SGX or enclave, it will provide you better confidentiality and the integrity, and that way policy will not be released to the public. And then for the anonymity network, the author uses the Tor network, and for Tor network is an onion ring. So when the request comes, it will go through an entry point and it will forward to the relay, and then it will go to the exit node and go to the destination. So this Tor network might be also vulnerable, those entry points. So for that, they again use the enclaves or SGX architecture, and within basically you can think about those entry points as a node, and those machines they will use the SGX, and within the SGX they create enclaves, and those enclaves will be using the remote attestation. They will establish the secure channel, and then they will start to communicate. Finally, I'm almost there. So finally, I want to talk about the trusted analytics from using the cloud. This paper was published in 2015 in Top Security Conference. So the idea here is they want to run the MapReduce job in the cloud, but they want to make sure that the MapReduce job is secure. So now let me introduce you Cloud.com, the Hadoop MapReduce things. So Hadoop is a architecture has two components: Hadoop distributed file systems, and then the MapReduce. So it follows the master-slave architecture. So we will have a bunch of master architecture where the job tracker and the name node, and then the slave architecture node will have the task tracker and the data node. The data will be stored there, and a large file will be split into a number of blocks, and the blocks will be stored into these data nodes. And then what the MapReduce job does, MapReduce will take those split inputs and process each record from those split, and then produce intermediate key value pairs. And those intermediate key value pairs will be shuffled over the network and then sent to the appropriate reducer. The key point here is intermediate key value pairs having the same key should end up with the same reducer, and then reducer will reduce it. And this is a famous example for the word count. You see apple, orange, mango. There is the apple 1, orange 1, and then mapper will make the key will be the word, and the count will be 1 in this case. And then this way it will be shuffled, and then all of this particular reducer will get all the apple keywords having the intermediate key value pairs having the same key. In this case, apple will end up with the same reducer. So in this case, they want to run this MapReduce job in the cloud, because nowadays people move their data in the cloud, and cloud provides better storage, but the cloud may leak confidential data in the code, and privileged insider may leak user data. Attackers may break into cloud data centers and steal the data. So these are the possibilities we have. So one approach is, why don't you encrypt the data on the disk? But that's not enough. Use the spot from general purpose computation. So when you run the general purpose computation on this encrypted data, that may not work. You can say, why don't you use fully homomorphic encryption, which will not be efficient in this case. So in this work, author tried to protect the MapReduce computations, ensures the confidentiality of the analytics code and the data. So in this case, analytics code means MapReduce code, and the MapReduce code will run on the data means the splits and so on, and ensure the integrity of the distributed MapReduce computations, because in a distributed computing, you know that some nodes may fail. You have to make sure the fault tolerance mechanism. And the idea here is, usually if you want to put one solution is, why don't you move the Hadoop MapReduce code into the trusted code base or the SGX enclave area. That's one possibility, but usually Hadoop code is very big, around 200, more than 200 lines of code. So you cannot put that huge amount of code into the enclave area, because again each enclave has a 100, at this point Intel has a 128 megabyte in size. So that will not work. So that's why the author proposed the trusted part of the code will go there, and a small software and the low overhead they encounter. Again, you will have let's think about MapReduce. You have a multiple mappers, and each map, one map task will be run in a single node, and that node where you will run the map code in a SGX enclave area, and this map code will produce, say, intermediate key value pairs, and those intermediate key value pairs will be shipped over the network to the reducer, and the reducer code will be run in an enclave area. That's the very basic idea. But but you may see when the data will be shipped over the network, there might be some sort of inference attack is possible also. Okay, so here we usually MapReduce code written in Java, but their case you wrote it in C++, and so enclave library code only 3,300 lines of code, and what they do in case of the mapper code, they say they identify the private enclave code that will reside only in the enclave area. And then this is the public enclave code. When the mapper, let's say this mapper emits intermediate key value pairs, that intermediate key value pairs needs to send to the over the network to the reducer machines. So in that case, this enclave code, private enclave code needs to send the data, and this communication will be carried out through the public enclave code, and that will communicate with outside of the enclave. Outside of the enclave will be communication. This communication with the outside of the world will be carried out through this part of the code. Okay, so this way the author carried out the operations, and they show that they have a reasonable result. And then also they have a verifiable unit. When the mapper produces some results, it is possible that mapper may fail, or maybe compromised for various reasons. Public code, so they will have a mapper summary will be generated periodically, and it will be sent to the verifier, and verifier will see whether certain objectives are achieved or not. And so in a nutshell, so these are the work so far people are doing, but one of the criticism for this work is when the data will be shipped over the network for shuffling purpose, then it will be prone for some sort of attack. So there are some subsequent paper that try to address that issues. So that's it. Do you have any question for this last part? Yeah.
I have a question to this SGX in general. You said there are 100 megabytes of this trusted memory,
128
right?
megabyte, yeah.
And if multiple applications want to use this SGX simultaneously, they have to share this 100
So
megabytes?
in a particular machine, you can create multiple enclaves.
And to each enclave there are
128 megabyte.
Okay.
But the plan is, I think Intel is going to release a new SGX version. They're trying to increase that memory size. But it may not increase that much, but it's still, that means when your data is too big, you have to partition it and load it part by part. And there is overhead when you do this step, because you have to do sealing, unsealing business. And that adds some overhead. But it is a very protected, and it averts a lot of attacks. But still, if the device, if there is a hardware attack happens, that means if the device is compromised, somebody comes and try to destroy the device, then that type of thing you cannot protect it. But if a software attack happens, then using SGX or the enclave area, you can avoid those type of attack easily.
Thank you.
Any other question? And this is first time I'm presenting this part. So anyway, thanks for your patience during the presentation. No question? Thank you.